Thank you. So the topic of my presentation is hydrothermal synthesis of two-dimensional nanoparticles for nanolubricant applications, a pathway for enhanced efficiency. So why nanolubricants at all? So lubrication, we know, is critical to the smooth functioning of the machinery and mechanical systems. Friction and wear are natural consequences when two surfaces in motion come in contact. And without proper lubrication, the friction increases, causing excessive heat generation, and mechanical parts wear out more quickly and cause breakdowns. So effective lubrication forms a thin film tissues. It prolongs the lifespan of the components, enhances losing their lubricating properties leads to increased wear and potential system failure. Then second challenge is efficiency in extreme conditions, high temperature, high pressure conditions. In high pressure or high load environment, the conventional lubricants often fail to maintain a consistent protective film, and their performance can decline rapidly also under low temperature conditions where they can become thicker or solidify also. Then the third challenge is wear resistance. It is seen that over time, the traditional lubricants may not provide adequate protection against wear, especially in systems that operate continuously under high stress. So to overcome these limitations and challenges, we can have nano lubricants, which is a next generation of lubrication technology. We can have enhanced thermal stability because nanoparticles present in the lubricants can withstand higher temperatures without degrading, maintaining the lubricant's performance in extreme heat. They can also dissipate the heat more effectively, reducing the risk of overheating in the engine. Then they also have superior anti-wear properties because they can create protective layer on the surface, minimizing direct metal-to-metal contact, which reduces the wear and prolongs the life of the machine parts. And the third advantage is friction reduction, wherein they can act as tiny ball bearings, reducing the friction between the moving parts, which leads to smoother operation and lower energy consumption. So let's see the key applications of nanolubricants. It's seen that almost every industry, automobile industry, requires the use of nanolubricants for effective performance. So we have automotive industry, aerospace, manufacturing, energy sector, etc. So let's see the comparison between the conventional lubricants and the nanolubricants. So in terms of properties, first property, thermal stability. The conventional lubricants are moderate in thermal stability and they degrade at higher temperatures, whereas nano-lubricants have high thermal stability and they are stable even at extreme temperatures. The wear resistance is limited for conventional lubricants, whereas for nano-lubricants it is superior. Then the friction reduction is adequate in conventional lubricants, whereas in nano-lubricants it is excellent and it also minimizes the energy loss. In extreme conditions, efficiency declines for the conventional lubricants, whereas the nano lubricants, the efficiency is consistent in all the conditions. And also the last one is environmental impact. The conventional lubricants are, because they are based on petroleum-based feedstock, therefore they are having less higher environmental impact and they are less sustainable. Whereas the nano lubricants can be used in lesser quantities and also they can be made from the biodegradable biological resources like castor oil, neem oil, etc., which are non-edible oils, and thus they are also environmental friendly. So how to synthesize the nano lubricants and how to add the two-dimensional nanoparticles and which method we should take into account. So hydrothermal synthesis or hydrothermal method for synthesizing nanoparticles is found to be the best method as of now, which can be used to make the nanoparticles, and then the nanoparticles can be added as additives in the lubricants. So to make the nanoparticles, we have these things to be done. First is precursor selection. We can select metal salts, either sulfates or nitrates or oxides, used as precursors. Then we had to prepare a solution. The precursors are dissolved in water or mixture of solvents, often under basic or acidic conditions, depending on the desired product. Then we had to seal it in an autoclave. The solution is then transferred to a Teflon-lined autoclave and then sealed. The autoclave ensures pressurized environment, and typically the temperature between 120 degrees Celsius to 250 degrees Celsius in the autoclave. Then the next one is reaction and cooling. The system is then heated for several hours or several days, depending on the type of nanoparticles to be made, promoting nucleation and the growth of two-dimensional nanoparticles in the autoclave. After cooling, the nanoparticles are collected, washed, and dried up. So we have made these 5 different types of nanoparticles using this method, and all the 5 are used in making of nanolubricants. So the first one is titanium dioxide. Then we have molybdenum diselenide, then tungsten disulfide, tungsten diselenide, and zinc oxide. So all 5 have shown good performance in the engines. So let's see about hydrothermal synthesis method for synthesizing nanoparticles, which are two-dimensional. So preparation of precursors. Then we have transferring to autoclave, which is Teflon lined. Then we have the autoclave is heated in a temperature between 100 to 250 or 300 degrees Celsius in a vacuum oven. Then the solution coming from that is transferred, kept for filtration. Then it is further dried in hot air oven at 60 degrees Celsius. And then finally, we have this white powder obtained nanoparticle. This is of zinc oxide. So what are the parameters used to control the hydrothermal synthesis method? So the first and most important parameter is temperature. We see that temperature is one of the most critical parameters. It drives the kinetics of the reaction and determines the phase and morphology of the product formed. The typical range of temperature is between 120 to 250 degrees Celsius, although some reactions, some nanoparticle synthesis may require higher temperatures. Then effects, higher temperatures, they increase the reaction rates and the solubility of reactants, promoting faster crystal growth in the autoclave. It also leads to the formation of more crystalline and larger particles. We see also that lower temperature in the autoclave gives finer particles and sometimes amorphous structures and useful for controlling the thickness in two-dimensional materials. So we observe that higher temperatures give crystalline materials by far, and by and large we get amorphous materials at lower temperatures. So we have to optimize. The temperature must be optimized to balance this nucleation and growth. Example, graphene oxide if you want to use to make nanoparticles, then it is recommended to have a temperature of 150 degrees Celsius to ensure good oxidation. Then if you want to use molybdenum disulfide, then higher temperatures are required between 200 to 250 Celsius to have good crystal formation, crystalline layer formation. The next parameter which is used in hydrothermal synthesis mechanism is pressure. Pressure typically auto-generated in the closed autoclave. It enables reactions at temperatures above the boiling point of the solvent, and the typical range of pressure is between 1 megapascals to 10 megapascals, depending on the solvent's vapor pressure at the reaction temperature. The effects of pressure, high pressure facilitates the solubility of the precursors easily. Then it also promotes the growth of larger and denser crystals. Whereas we see that lower pressure is useful for synthesizing porous structures or thin films. Then optimization is required again in this. So pressure is indirectly controlled by adjusting the solvent volume and the reaction temperature, maintaining a sufficient fill factor, typically between 60 to 80% of autoclave volume, ensures optimal pressure. The third parameter is reaction time. It dictates how long the reactants are subjected to high temperature and high pressure environment. And the typical range is between 6 to 72 hours, depending on the material which we want to synthesize nanoparticles of. Then the effects of long reaction time, it enables complete crystallization and the growth of larger particles, nanoparticles, useful for production of defect-free structures in the nanomaterials. Whereas we see that shorter reaction times give smaller particles or intermediate phases like clusters, etc. And it also favors rapid nucleation over the crystal growth and useful for the size control as well. So again, we had to optimize, and it is observed that for molybdenum disulfide nanosheets, two-dimensional nanoparticles, it requires around 24 hours, whereas zinc oxide nanocrystals can form within 6 to 12 hours. So depending on different types of materials, we have different optimal times. Then the last parameter is precursors which are used to make the particles, nanoparticles. So precursors provide the necessary elements to control the chemical composition of the final product. So examples, metal salts if you use, it gives metal ions like metal salts like nitrates, sulfates, or chlorides. Example, MoCl5 for making MoS2 nanoparticles. Similarly, if you use chalcogens, they provide sulfur, then selenium or tellurium for sulfides, selenites, etc. The solvents can be deionized water, although we can also use organic solvents for specific reactions. Then the effects of the precursors. The purity of precursors is very, very important. Impacts the chemical composition and properties of the finished product, nanoparticles. Then we can also use surfactants. If you use surfactant, it can direct the growth of nanoparticles into specific shapes, such as nanosheet or nanorods. So as we discussed before, there are different types of nanoparticles, zero-dimensional, one-dimensional, two-dimensional. So for the application of nano lubricants, we prefer using two-dimensional nanoparticles. To have two-dimensional nanoparticle morphology in the autoclave, we require the use of surfactant. So again, optimization is a key factor. So example, sulfur source like thiourea can be paired with molybdenum salt for making of MOS2 nanoparticles. Similarly, we can also use ammonia or urea to adjust the pH, and pH also can influence the morphology of the final formed nanoparticles. So these were the 4 different parameters which can control the reaction in the autoclave. Now come to the instruments which can be used to characterize the nanoparticles formed from hydrothermal synthesis. So this will move forward quickly because this is just description of the instruments. So first one is SEM, scanning electron microscope. If you use field emission scanning electron microscope, that gives added advantage. Then you can also use TEM, transmission electron microscope. Then X-ray diffraction, Raman spectroscopy. So these 4 methods can be used to synthesize the nanoparticles and also characterization of nanoparticles. So then let's see the synthesis of nanoparticles using this hydrothermal method individually. So start with zinc oxide nanoparticles. So we have added 50 ml of 1 molarity zinc-based solution. Then zinc nitrate was taken. Then it was precipitated. Then the mixture was stirred. Then we have used hydrothermal processes for synthesis of nanoparticles, and we kept a temperature of 120 degrees Celsius for a period of around 4 hours. Then at the end, we have taken out the product from the hydrothermal synthesis, then centrifuged at RPM of 6500, then for a period of 20 minutes for 5 times. Then we did drying and grinding, temperature of 80 degrees Celsius for 24 hours. And finally, we got the finished product. So coming to WSE2 nanoparticles, here we have used NaBH4 as a precursor. Then we have used selenium powder and this chemical, and then transferred to the autoclave, which was Teflon lined. Then there was hydrothermal reaction. The temperature of hydrothermal reaction in this case was 200 degrees Celsius, and the time was 48 hours. So then tungsten disulfide nanoparticles, here the precursor used were WCl6 and TAA, and then it was kept in autoclave. The temperature was 220 degrees Celsius, and the time was around 20 to 24 hours. Then coming to TiO2 nanoparticles, here TTIP solution was a precursor, and here the temperature in the autoclave was kept at around 180 to 200 degrees Celsius, and the time was around 12 to 24 hours. So here the duration of the time and the temperature that influence the crystallinability and the morphology of the TiO2 nanoparticles. So if you do analysis using SEM, so the instrument we used, SEM instrument was made from Z's, and we saw that polyhedral shaped, like hexagonal, pentagonal, and also spherical shapes were observed from the nanoparticles formed, and they were homogeneously distributed and having uniform size morphology for especially metal oxides. These above SEM images represent TiO2 nanoparticles. Then we have ZNO nanoparticles and tungsten disulfide nanoparticles. So then it was observed that we had good nanoparticles formed of good morphology. Similarly, here this image shows tungsten diselenide nanoparticles, and here we have molybdenum diselenide nanoparticles. So everywhere we saw, for all the 5 different samples, we saw good yield and good morphology of the formed nanoparticles. So now let's see the advantages of hydrothermal synthesis method. We see that it gives controlled size and morphology. Then we have good temperature and pressure regulations. We can fine tune, and accordingly we can get the good growth rates of the nanoparticles formed. And also we have control of the size or the particles. Then higher temperatures typically promote faster crystallization, while controlled cooling can also help to achieve specific shapes like nanosheets or platelets. So the role of surfactants and templates cannot be underestimated. Surfactants, capping agents, and structure directing templates can be incorporated as well into the reaction mixture initially before adding the autoclave. And these additives can guide the growth of particles, nanoparticles, into specific morphologies like hexagonal or square or irregular two-dimensional sheets, etc. Further, we can also have homogeneous growth environment inside autoclave using hydrothermal synthesis method. We see that the sealed and pressurized environment in hydrothermal synthesis system ensures uniform conditions throughout the solution, and this also prevents the uneven growth, and the yield of the particles are with consistent shape and size. We also have reduced agglomeration, because once the particles get agglomerated, we don't have nano size. It goes to 10 to minus 7 or 10 to minus 6 meters size, but we want nanoparticles. And agglomeration also has a problem that later on when we mix this in the lubricants as additive, so then they will not be uniform mixing, and it will also interfere with the engine performance. So therefore, we don't want any agglomeration. So this hydrothermal synthesis method minimizes the agglomeration due to the liquid phase synthesis method, producing well dispersed and distinct nanoparticles, which is critical for the two-dimensional materials, where individual layers must remain separate for optimal performance in the lubrication. In addition, we also have high purity and stability of the finally formed nanoparticles. Hydrothermal synthesis is also known for producing materials with high purity and structural stability. Further, we have minimal contamination because the system is closed, autoclave is closed, sealed. So this closed reaction system minimizes the exposure to external environment, external contaminants like dust or air impurities, ensuring clean synthesis environment. Further, the use of pure precursors as raw materials, reactants, and controlled reaction pathways also enhances the chemical purity, because we don't have any side reactions or undesired reactions here. Then we also have selective crystallization. Under high temperature and pressure conditions, only certain crystalline phases are favored. This selectivity reduces the likelihood of forming unwanted byproducts or amorphous phases. As we saw before, in the temperature and pressure case as a parameter, we saw that high temperature and high pressure gives crystalline nanoparticle formation, and lower temperature and lower pressure gives amorphous nanoparticle formation. So that also we can control, and we can have crystalline nanoparticles coming out. Then stability of the materials. Nanoparticles produced by this method often have high crystallinity and lesser structural defects. Leads to enhanced chemical and thermal stability, which is very critical for use of two-dimensional nanoparticles in the demanding environments of high temperature and high pressure environments of the lubricants. Then morphology and size distribution of the nanoparticles synthesized by the hydrothermal synthesis method. This method allows for the synthesis of nanoparticles with well-defined tunable shapes like spherical, rod-like, or plate-like morphologies. The factors like temperature, pressure, and the type of precursors used can influence the final morphology or the product form. Controlled crystallization growth rates in hydrothermal synthesis often results in high crystallinity and uniformity in the structure. Then coming to size distribution, the particles which are synthesized through this method have good size distribution, very narrow range size distribution, because we have already controlled very precisely the reaction conditions. Then the adjustable parameters like reaction time, precursor concentration can fine-tune the particle size, which usually range from few nanometers to few hundreds of nanometers. Then coming to surface roughness and chemical composition of the materials, we see that the surface texture of the hydrothermally synthesized nanoparticles is influenced by the factors like temperature, temperature, pH, and the growth inhibitors used during the synthesis. So hydrothermal synthesis method can give smooth or textured surface depending on the crystallization process, which is very, very important for the lubrication application especially. How? Because if the surface is rough, the nanoparticles are formed are having roughness in the surface, then during the engine performance, engine operation, this will corrode, this will collide with the engine, and then it also hampers the life or decreases the life of the engine. Therefore, you want smooth nanoparticles. So this also is ensured in this method. Then chemical composition. The hydrothermal method allows for precise control over the material's chemical composition, enabling the incorporation of dopants or modifications at a later stage as the need arises. The high pressure, high temperature conditions often result in pure phase and stoichiometrically accurate materials. So now coming to, so we have synthesized the nanoparticles for the lubricant additions. So now let's see how the lubricant properties can be enhanced by using these nanoparticles. So we have reduction in the friction coefficients. So lubricants reduce the direct contact between the surface by forming a film, minimizing the mechanical interlocking and adhesive forces, and this reduces the shear force needed to slide the surface against each other. So key factors, the lubricants we know is viscosity and the use of additives, especially the friction modifiers, which can reduce the sliding resistance. So formation of protective tribofilms in the lubricating application. So the tribofilms are thin solid layers formed in situ during the operation, during the sliding or rolling contact due to the chemical reaction between lubricant and the surface materials. And these films, tribofilms, act as barrier, protecting the underlying surface from wear and oxidation. So the key features of these tribofilms, they are self-repairing, they continuously form under active tribological conditions, and they often consist of oxides, nitrides, or other reaction products. We can also use some additives like zinc dialkyd thiophosphate, which can be used as an anti-wear additive, which can form sacrificial layers during the lubricant operation. Similarly, you can also use solid lubricants where the materials like graphite or MOS2 can contribute to tribofilm stability. It also lowers the wear rate, increase the performance in extreme pressure, high temperature, also enhanced load carrying capacity. So we just move forward with the further advantages. One of the last slides. Advantages and limitations of nano lubricants. So we have reduced friction wear, higher thermal stability, lower cost synthesis. However, we have one challenge, that is in terms of dispersion. While dispersion techniques can improve the stability and maintaining uniform dispersion in base oil, it remains a challenge. So to disperse, we can use ultrasonicator to have uniform dispersion. And also we should ensure that this dispersion remains stable. The dispersion of nanoparticles inside the lubricant remains stable at extreme conditions of temperature and pressure. So final conclusion, the future of nanolubricant enhancement through this method of hydrothermal synthesis of two-dimensional nanoparticles hinges on strong collaboration between academia, industry, and other stakeholders. So as academicians, we can drive the fundamental research, the discovery and innovation, while industry scales up and commercializes the advancements. The benefits of these collaborations extend to lubricant manufacturers, end users like industrial and automotive sectors, and even environmental regulators. And this also spans across the material synthesis, which type of nanoparticles we want to synthesize for this particular application, performance testing in different engines and different conditions of temperature and pressure, and sustainable manufacturing, and the development of smart lubricants. This ensures that nano-lubricants can be integrated to real-world applications to enhance efficiency, sustainability, and overall performance. So thank you very much for giving this opportunity. I conclude my presentation here.